Okay, so I want you to draw 3 different graphs where your derivative is positive. 3 different graphs where all 3 graphs the derivative is positive. You're drawing a function.
Every point being positive.
Well, I want the derivative to be positive, which means it has to be.
Well, like, I mean, like, you don't want the derivative at all as 0.
No.
I mean, okay.
Derivative is always positive. Thank you. Okay, here are 3 different graphs for our derivative being positive. Okay, what I want you to notice, and I'm just going to erase this portion of it, okay? These are all increasing, but they all look different. What is true about the slopes in this graph? Our slopes are constant. Very good. What is true about the slopes in this graph? Our slopes are getting smaller, right? What is true about the slopes in this graph? They're getting steeper, which means they're getting bigger, right? Okay. These 3 different pictures, okay, they all have different second derivatives, okay? Our second derivative describes how our slopes act. Do our slopes stay constant? Do our slopes increase? Do our slopes decrease? Okay? When our slopes increase or decrease, this is what we call concavity. All right? Concavity describes the curvature of the function. Okay? And that is what was different about Sammy's second and third picture. One was concave up and one was concave down. To remember the difference, concave up would hold water, concave down would spill the water out. Okay? So like this parabola is all concave up, this parabola is all concave down.
I think so.
Sometimes it helps. Whatever I can do to help. Okay, so let's talk about this. F prime tells us how the y values are changing. When we look at the first derivative, it tells us whether our function is increasing or decreasing. Our second derivative tells us how the slopes are changing. That was the idea we talked about on the first slide. Okay, if our slopes are increasing, we are concave up. If our slopes are decreasing, our function is concave down. So I'm gonna draw some tangent lines on this concave up picture, okay? This is concave up. What kind of slope do we have right here? Positive or negative? Is this slope positive or negative? Negative, right? It's going down, okay? As I draw more slopes, they get less steep. So if negative slopes are getting less steep, that number's getting smaller. What's that slope? 0. Excuse me, that number's getting bigger, I misspoke. As our negative slopes get less steep, that number's getting bigger towards 0. And then once we get to this side, these slopes get steeper and steeper and steeper. Our slopes are increasing. Okay? Opposite thing happens here, concave down. As I draw these slopes, they get less steep and less steep. These numbers are decreasing. Then we hit negative. The steeper it gets, the smaller the number is. Okay? So concave up, our slopes increase. Concave down, our slopes decrease. Okay? So, how do we use the second derivative to help us? Do you have an idea, Cole? Okay. What did we do with our first, like if I asked you for increasing and decreasing intervals, right? You found the first derivative and figured out where it was positive or negative, right? If I ask you for concavity, what do you say? We find the second derivative and figure out where the second derivative is positive or negative, okay? Okay. If our second derivative is positive, we are concave up. If our second derivative is negative, we are concave down. If our second derivative is positive, we have no curvature. Now, our graphs will not always remain concave up or just concave down. It is possible for our graphs to switch concavity. Okay? When we talked about our function switching, increasing to decreasing and vice versa, those were minimums and maximums. Where our function switches concavity, those are called inflection points. And much like minimums and maximums, inflection points could occur when the second derivative is 0 or undefined. Is there a glare? Yeah. Okay. Hasn't been sunny the past couple days. Okay. So inflection points are where the concavity changes. Inflection points can only occur where the second derivative is 0 or undefined. Okay? Now, the second derivative could be 0 or undefined and we not have an inflection point, but they only can occur when our second derivative is 0 or undefined. This feels all very familiar, doesn't it? Okay, what? Except with the second derivative. Yes. All right, so I'm going to show you 4 pictures that all look very different. We're going to talk about what are inflection points and what would not be inflection points, okay? So here are 4 graphs, okay? Here, and this is probably what you're going to see most often, a nice smooth inflection point, okay? This is an inflection point. Here the second derivative is 0, okay? This is an inflection point. We switch from concave up to concave down. That inflection point is that corner. Here, we're going to get like a 0 or undefined for our second derivative here, but we don't switch concavity, so it is not an inflection point. You see how it's concave up on both sides? Okay. Here, we have concave down and concave up, so the concavity switches, but it switches at the asymptote. An asymptote can't be a point of inflection. It changes concavity, but it's not an inflection point. So today we're focusing on intervals of concavity and inflection points. It's going to feel very familiar. It's going to be very similar to what we did on Tuesday, except we're dealing with the second derivative. Okay? So we will start off simple. Josh, what's our first derivative?
3x minus 3.
Good?
Squared. Yeah.
Oh, 3x squared. Jennifer, what's our second derivative then?
6x.
Okay. Now, only our first derivative do we find critical points. With our second derivative, we just say we're finding potential points of inflection. Okay? And those occur when our first derivative or second derivative is 0 or undefined. Can our second derivative be undefined? No. So we're only worried about when it's 0, which is at 0. What, Cole?
No.
Oh.
Oh, yeah, no, I just.
So we're going to do the same thing, but notice how I'm labeling my number line as second derivative. And we'll put our potential point of inflection on our number line. Okay. We're going to plug in values to which function? The second derivative. That's what we're testing. So if we plug in -1, our second derivative is? If we plug in +1, our second derivative is? Positive. Second derivative. Where the second derivative is negative, we're concave down. Where the second derivative is positive, we're concave up. Okay? So we would write that we are concave up from 0 to infinity and concave down from -infinity to 0. Do we have a change in concavity? We sure do. since we changed from negative to positive on our second derivative, we know that x equals 0 is where our point of inflection is. I'm going to abbreviate because that's a lot of letters to write. Point of inflection. Are you okay with that abbreviation? Okay. So our point of inflection is when x is 0. If we plug 0 into our original function, we get -4. That's the coordinate on our graph where our concavity changes. For fun, let's look at it on a calculator. Are you laughing because I said fun? Okay. Okay. Here's our graph. Notice how we're concave down. I was going to say, thank you. Like, that's not right at all. Okay. Here we go. Notice how we're concave down. At 0, -4, we switch to concave up. Questions?
So we use the second derivative to talk about concavity of like just a function.
Yes. Okay. Let's talk about the relation to the first derivative. If we're concave up, that means the first derivative is increasing. Our slopes are increasing. But it means our function is concave up. Okay, I'm going to go a little out of order, and I'm changing this one. To x to the 2/3. Gina, what is our first derivative? Two-thirds x to the -1/3. Great. Our second derivative, Jake. Mm-hmm. Good. All right. Now, if I had you also finding increasing and decreasing intervals, okay, you would have rewritten this to be 2/3 to the 1/3. If you have to find the second derivative, go back to this form and use the power rule, so you don't have to do the quotient rule. Okay, that would be much easier, much more time efficient. Okay. But anytime that you're having to find where your derivative or second derivative is 0 or undefined, it's in your best interest to rewrite any negative exponents as positive. So now we need to know where is our second derivative 0 and undefined. Can our second derivative be 0? It cannot. Our numerator is -2. -2 can't be 0. That's not a problem. Okay. Our second derivative is undefined where? Reagan? At 0. If we set our denominator, equal to 0, our possible point of inflection would be 0. So on our number line, remember we're labeling it as our second derivative, 0 here. Okay, let's talk through x to the 4/3 means what? Yes, I am getting there 2 steps ahead of me. What does the 4 and the 3 mean, Austin?
Fourth. Raise
Just raise it to the 4th.
it to the fourth, and then cube root.
Okay, so this means we raise it to the 4th power and then cube root it. So Austin pointed out if we're raising it to the 4th power and then cube rooting it, that's always going to be a positive number. Do you agree? Okay, so if we plug in like a -1, what is the value of our second derivative going to be? Positive or negative?
Well, negative, because there's a negative sign. You're multiplying by 2 times.
Mm-hmm. So x will be a positive number, but it's -2 over 9 x to the 4/3. What about if we plug in something above 0? What's the value of our derivative going to be? Still negative. Okay, so let's talk about this situation here. First of all, our function is not concave up. Our function is concave down, but you are not going to write negative infinity to positive infinity. Is our function concave down at 0? No, there's no curvature at 0. So you have to break this up into 2 different intervals. Do we have a point of inflection? We do not. Our second derivative does not change sign value, which means our function does not change concavity. If we graph this, was it x to the 2/3, right? What do you think is happening at 0? Any guesses? Huh? Asymptote or a what else is possible? Or a corner. And next week we'll get into figuring out which is which, okay? But there is a corner at x equals 0. Notice how we're concave down, concave down. Good question.
Well, if you have an asymptote, it's always not going to be. It's not going to be a point of inflection, but if it's
True. Yeah. Yeah, if that were an asymptote, even if it changes concavity, it can't be a point of inflection. Let's talk about how would we know if there was an asymptote in our original function? Are you saying something? How do we know if there's an asymptote in our original function? How do you mean a whole?
Oh, well, that's what I mean, if you can't factor it out.
Okay, but what characteristic? There needs to be a denominator where your denominator is 0 in your function. That's where there's an asymptote. Okay, so this one wasn't going to have an asymptote because there's no denominator in our function. Okay, but if there was like x plus 4 in the denominator of our function, at -4 we'd have an asymptote. Okay. All right, for this example, I'm going to have you go ahead and ignore this. We're going to go ahead and go through increasing, decreasing. No, we're not. We're just going to go through concave up and down. All right. Abram, what's our first derivative?
4x cubed minus 6x squared.
Our second derivative. Aaron, what is it?
12x squared minus 12x.
Okay. So when we set this equal to 0, we can factor out in 12x. Cole, what are our possible points of inflection?
0 and 1.
So we have a second derivative number line with 0 and 1. If we plug in a negative number, what's going to happen to our second derivative? What kind of value will it be? Positive? What about between 0 and 1, like 1/2? You'd have like 12 times 1/4 minus 12 times 1/2. What's that going to be? Negative. And then a number greater than 1 to give you positive, right? So we are concave up from negative infinity to 0 and 1 to infinity. We are concave down from 0 to 1. How many points of inflection do we have? 2. There are 2 times where our second derivative changes sign value. So we have points of inflection at x equals 0 and x equals 1. To find those coordinates, where do we plug 0 and 1 into? The original. So when we plug in 0, we get 5. What do we get when we plug in 1? 11?
Oh, wait.
With your thumbs, how do you feel? Okay. Good. Now, where it gets exciting is where we get to look at graphs. Okay. Here is a function graph. That is up to you. We're going to identify all of these things. Okay? So on our function, okay, Joe, where are we increasing? And that would be it, right? Yes. So then, Sammy, where are we decreasing?
Does it end at those points or does it keep going?
We're just going to say that it ends.
Alright, so -5 to -2. And then 1 to 3.
Okay, good. That's where we're increasing. That's where we are decreasing. So, Josie, do we have a relative minimum? At -2, -1, we have a relative minimum. Madison, do we have a relative maximum? At 1,5. Okay, great. Concavity. Okay, Trevor, where are we concave up?
-5 to -3. -2, -1.
Do you agree with Trevor's concave up? -4 to -3, -2 to -1. Which means we're concave down in the other places, right? -3 to -2 and -1 to 3. Okay. So Isaac, St. Pierre, where are our points of inflection?
-3, 1.
And -1, 1. Okay. Identifying the information from a function graph, not so bad. It's very straightforward. Here's where it gets fun. This is a derivative graph. Okay. Increasing means our derivative is positive, right? So Larry, where's our derivative positive?
26.
Oh, right.
We'll just say 8 to 9, okay? Good. So Michael, where's our derivative negative?
0 to 1. 6 to 3.
Okay. Good. Jake, do we have a relative minimum?
At 1 and 8.
At x equals 1 and x equals 8. Very good. Do we have a relative maximum, Abram?
Equals 6.
Yep, at x equals 6, because our derivative is going from positive to negative. Okay, so that's, you guys practiced that yesterday. So here's the new stuff, concavity. Remember, concavity means what are our slopes doing? Are our slopes increasing or decreasing? So where our function is concave up is where our derivative is increasing. Okay, so Logan, where's our derivative increasing?
0 to 2
Okay,
and 3 to 5 and 7 to 9.
okay. Our derivative is increasing, which means our function is concave up. Okay. Our derivative is decreasing where, Alex?
2 to 3 and 5 to 7.
Okay. Our points of inflection occur where we change concavity. So since our derivative is changing from increasing to decreasing, we have a point of inflection at x equals 2, x equals 3, x equals 5, and x equals 7.
So just change the
Yes, exactly. Question. So your homework is on your gold sheet. I'm also going to have you do 1 and 3 from this pink sheet. So what's on the board, what's on your gold sheet, and then 1 and 3 from this pink sheet. 2 and 4 is going to be your warm-up tomorrow. Everyone get a pink sheet? Yeah,
Can we go back like 4 slides?
4 slides. This one?
Yeah. So what would you, so for the second derivative,
Uh-huh.
What would you get if you plugged in -1/2?
You get -1/2.
Yeah.
You get 12 times a positive 1/4 minus 12 times -1/2. So it'd be a positive plus a number. Does that make
Yeah.
sense? Okay.